Topic 2 in Unit 6 is about solving systems of equations by substitution. Substitution is the second method that we're going to learn about how to solve a system. So previously in Topic 1, you learned about how to solve a system by graphing. So you would take two different equations, you would graph them on your screen, and you would find their intersection, and that point was considered the solution. And remember that points are always written as x, y. So that should help you kind of remember the definition of a solution to a system of equations, which is a coordinate. I'm going to write x, y underneath it. That makes both equations true. Okay, so graphically that looks like the intersection point, but when you're thinking about just the equations, it's an x value and a y value that you can plug into both equations, and it makes both equations true. It makes them both work out. So we're going to hop right in, but you'll notice that this entire notes page is lacking in graphs. We have one on number 12, but we're going to do all of these without a graph. Now, does that mean that you couldn't do them with a graph? Absolutely not. You could take all these problems, graph them on a coordinate grid, and find your solutions that way. But it's just good to know multiple different methods to solve systems, as some of them are easier than others depending on what the problem looks like. So for example, on number 1, this equation right here, in order to graph it, we'd have to change it into slope-intercept form, and maybe there's a faster way that would prevent us from having to do that work. So we are going to use substitution. Well, looking at number 1, we have two equations. We've got an x, we've got a y. You may say, oh, there's no y on the first problem, but I could easily just say plus 0y, right? So we do have an x and a y, and we're ultimately trying to find a solution, a coordinate that has an x and a y value. Well, when I read the first equation, it literally says x equals 3. In other words, x is 3. They just told us the first number, 3, okay? Well, if x is 3, well then when I look at this bottom equation, instead of an x, I'm going to write x is 3 and just plug it in. Well, if I know that number, then I've created an equation that only has one variable, and I can just work this thing out, simplify, and then solve to find the value of y. So I am solving my equation, and I see that y equals -3. Problem solved. The end. Okay, now we did technically use substitution just then because we substituted the value of 3 into the x. So let's try that again on number 2. This one isn't quite as clear, but again, I have two equations. I have x's and I have y's. Again, the top equation you could always see as adding like a 0x onto it or something like that. So we've got our x's and y's. We now just need to substitute to solve. Well, that means I need to find what x or y is equal to in order to substitute it into the other equation. Well, if I look at this top equation, 3y equals -6, I can easily solve that to figure out what y is equal to. Y is equal to -2. In other words, y is -2. Well, if that's the case, instead of writing a y here, I can just write -2. Then I just have to work this problem out, simplify and solve, and x equals 2. So I have now found my solutions to both of these systems without using a graph and just simply using our knowledge of substitution and how variables work, okay? But again, if you wanted to, you could graph these two equations. So this top one would be a HOI, technically, if you divide both sides by 3. So it'd be y equals -2 down here. The bottom equation, we'd have to solve it for y, so that it looks like y equals mx plus b. We'd get what? Y equals +1/2 x -3 maybe? I don't know. I'm trying to not waste too much time on this, but something like this. And there would be our solution point of 2, -2. Okay, so you can still solve all of these graphically, but this is just a different method that might be a little bit easier in some cases. Okay, so let's keep on trucking. It says consider the systems below what is different. Solve for the solution. We'll look at number 3. What is different about this problem? Well, for number 3, I've got an equation with an x and a y, and I've got another equation with an x and a y. So if I'm wanting to figure out what one of the variables is equal to, I'm not actually able to do it yet, right? I can't just solve one of those equations to where I find out the y is 12 or x is -3. I'm not able to do that yet because I have too many unknowns here. However, I can still use substitution. So looking at number 3, I see that y is 2x. Those are the same things. Y is equal to 2x, so y literally is 2x. So I'm going to plug that in for y. So when I go through here to write my equation, 2x plus 5, instead of writing y, I'm going to write 2x because I know that they are the same thing based off of the second equation, equals -12. Well, now that I've done that, I'm able to just, again, simplify the problem and solve and determine what x is equal to. So 2x plus 10x equals -12. So 12x equals, -12. We divide by 12, x equals -1. I have now found part of my solution. And again, I used substitution because I substituted one value of a variable into the other. It just so happened that when I substituted, I just kept that x with it because I didn't know what x was. Now that I know what x is, I'm just going to go plug it right back in to one of my original equations and solve to find what y is. So I'm going to use the bottom equation just because it's shorter. So y equals 2x. Well, if that's the case, then y equals 2 times -1. So y has to equal -2. Okay? Now again, if you're unsure, you could always graph these. You could put them on a coordinate grid and see where they intersect. But sometimes substitution is actually a little bit faster. Okay, so number 4. Same thing. I look at my equations and I see that I have 2 variables in my first equation, 2 variables in the second equation. So I'm going to use substitution because I have the x by itself. This x is already isolated on its own, and I can see what it's equal to. X is equal to y plus 4. Well, if I know what x is, that means I can substitute in for x. So let me write this equation, but when I get to the x portion, I'm not going to write the x, I'm going to write y plus 4. Because that's what x is equal to. Then I finish out writing the rest of the equation. I'm going to distribute, because I've got these parentheses here. So 2y plus 8 plus 3y equals 23. Combine like terms, subtract the 8, and y equals 3. Okay, so I have found part of my answer. Now again, just like the problem before, I'm going to take that answer that I have found and go plug it back into one of my original equations to find out what x is. So if I know that x is equal to y plus 4, well, now I know what y is. Y is 3. So x has to equal 7. Okay. So let's try number 5. If you feel like you're starting to get the hang of it, always feel free to pause the video, work ahead, then resume, maybe fast forward a little bit and see if we get the same answer. So for this problem, again, I want to use substitution. This is literally a lesson about substitution, so that's the goal here. I see that this y has been isolated. It is by itself, and it is equal to 2x minus 10. That's what I'm going to plug in to the y in the other equation. Okay, so I'm going to go ahead and write 4x minus 3, but when I get to the y, I'm not going to write y. I'm going to write what it's equal to, 2x minus 10. Then I'm going to continue. We're going to distribute. And combine like terms and solve. Then once you have one answer, x equals 3, we're going to plug it in to one of our original equations and get our answer. So the bottom equation says y equals 2x minus 10. Well, now I know what x is. X is 3. So y is 6 minus 10, so y has to be -4. Okay. Alrighty, number 6, again, same thing. This would be a great one to pause. Try it out yourself, see if you're understanding what's going on, and then just resume to see what answer I get. So I want to use substitution. I see that this y is by itself. So that means I can plug in x plus, instead of y, I'm going to write what y is equal to, which is 2x plus 3. Then I combine like terms, move that 3 over, so x is equal to 1. Then I'm going to plug that answer back in. If 2x plus 3 equals y, and I know that x is just 1, then y has to be equal to 5. Okay? Alrighty. Those were the basics. But now the second page takes things up just a notch. Not very much, but just a little bit. If you look at number 7, we're still wanting to use substitution, but something isn't quite as pretty about this problem. The issue is that we don't have a variable that has been isolated on its own. So we need to just do a little bit of manipulating to get one of the equations where x or y is isolated on its own. So I'm thinking this bottom equation should be pretty easy to isolate the x, because all I need to do is add that y over to the other side. So x is equal to 8 plus y. Okay, so I would rather work with that equation than this one. So I'm just going to cross it out. It's still there. It's still important to remember as the original equation, especially if you've made a mistake. But I'm going to focus on using x equals 8 plus y, because that means I have now isolated the x and I know what it's equal to. So I can go plug that into the other equation. So 2 times, instead of x, I'm going to write 8 plus y. And then I'm able to substitute just like we've been doing. So you'll distribute. You will combine like terms. Move that 16 over, and you get y equals negative 20. Then to get the x, remember you just go plug it back into one of your original equations. You can use the actual original equations, the ones that are printed here on the paper, or I can use this other equation that I made for the x, because it's really just this same equation, but manipulated so the y's on the other side. So if I do that, x is going to equal 8 plus that y that I found, which is negative 20. So that means x has to equal negative 12. Okay, so number 8, same thing. If I look at this problem just right off the bat, I see that I don't have any variables that have been isolated. So I need to pick something to rearrange so that I have a variable by itself. So if you're looking at them, if I was to get like this y by itself, I'd have to move the 2x over, I'd have to divide by 2. I'm thinking that's not the best option. What would be better is to use one of the bottom equation and move one of these variables over to the right-hand side. It doesn't matter which one. You can totally do it either way. In fact, I'd encourage you to maybe make a call right now. And if I choose a different one, don't redo the problem. And let's just see if we get the same answer, because we should. So I'm going to actually move the x over. So y equals 3 minus x. Okay. And again, I'm just going to, for my own sake, cross through that and focus on using this new equation I just created. But again, they're the same thing, just manipulated differently. So now that I have this, I can see that I want to plug this in for y in the other equation. So I'm going to write that top equation, but instead of writing y, I'm going to write 3 minus x plus 2x equals 4. So 6 minus 2x plus 2x equals 4. Now we combine like terms, so negative 2x plus 2x is 0. That makes 0, so 6 equals 4. What happens when we get 6 equals 4? That is a false statement, right? When things are false, we usually write the answer, no real solutions, right? Well, that has not changed in this case, okay? Remember that we talked about in topic 1 that if you have two parallel lines, they're not going to intersect. They're not going to have a solution, a shared x and a y that will work. So let's just go ahead and solve this first equation for y equals mx plus b and see what happens here. So I'm going to move that 2x over by subtracting it, and I'm going to divide both sides by 2. So y equals negative x plus 2. Well, really, this one is y equals negative x plus 3. Picture those on a graph. If I have two equations that both have a slope of negative 1, one going through 2 and one going through 3, they're never going to touch. So you'll notice, just like when we solved equations back at the beginning of the year, this false statement thing still holds true. If you get a false statement, it still means no real solutions. It means that these lines were parallel lines and they don't have a shared solution. Okay? All right, number 9. I know this video is getting long. I'm going to keep walking through these individual examples, but just you know yourself and you know what you need review over and what you don't. So feel free always to pause, fast forward, put it on triple the speed, whatever you need to do to make sure that you are learning in the way that makes sense for you. So on number 9, we have x equals negative 5/3 y and then negative 2x plus 5y equals 25. I'm guessing when you first see this problem, you're thinking, oh, there's another fraction, right? Well, we're going to deal with that fraction in just a minute. We're going to go ahead and still substitute, just like we always have, into the other equation. So I've got negative 2 times negative 5/3 y plus 5y equals 25. At least it was already isolated for us, right? The x. Okay, and I'm going to go ahead and still multiply this out. So negative 2 times negative 5/3, just remember that's got a 1 underneath it. So I get positive 10/3 y plus 5y equals 25. Okay, now at this point, here is where I'm going to get rid of that fraction. I don't want to deal with the fraction anymore. You hopefully have talked about already in your classes this year how to clear a fraction. I'm going to multiply this entire equation by a number, a whole number, that will eliminate the fraction and keep everything as a whole number. I'm going to do that, or an integer, I guess. I'm going to do that by multiplying by the denominator in this case, just the 3. Okay, doing so, again, this has a 1 underneath it, will create 30 over 3, which is just 10y. That's why we say that these cancel, okay? But I'm also still going to distribute this all the way across. So I've got 15y equals 75. Now I'm able to combine like terms, divide by 25, and I see that y is just equal to 3. Okay, so the fraction was not the end of the world. I still worked with it a little bit just to keep my substitution part intact. I don't want to mess up the substitution process by trying to clear the fraction too early. But as soon as you have just a one equation with one variable that you're working with, you can get rid of that fraction and try to make numbers a little bit easier for you. Okay, now I'm going to take the 3, I'm going to go plug it back in. I'm actually going to go ahead and stick with that one that's got the fraction, because if I multiply negative 5/3 by 3, we just get negative 5. There's my answer. Okay. Number 10. This problem is very simple and straightforward as far as this first part is concerned, but notice it asks you to do an additional step. It says then x plus y equals what? So our first step is to solve it and figure out what is x and what is y, but then our final answer is actually going to be whatever x plus y is equal to. So I'm going to take all of this, plug it into x just like we've been doing. I'm going to distribute. I'm going to combine like terms. I need to move my variables to one side. So I've got 9y equals 15. Ooh, did I do this right? Let me pause. Nope, I was doing this question correctly. I just always like to double check if I feel like it's not super simple of an answer, but we're doing this correctly. So 15/9, if I divide those both by 3, we're going to get 5/3. And that is the value for y, which is kind of yucky, but it's okay. We're going to manage. I'm going to plug that back in to one of my original equations. So I'm going to use that bottom one. It doesn't matter, by the way, but the bottom one already says x equals, and that's what I'm trying to get. So 4 minus 3y, which I now know is 5/3. So x equals 4 minus, well, here's where this gets a little bit easier because these 3's actually cancel each other out once you've actually done the multiplication. 3 times 5 is 15. 3 times 1 is 3. 15 over 3 is 5. So then x equals 4 minus 5, which is negative 1. Okay, now here's where the problem is not finished. So remember that they asked us, then x plus y equals what? So they're wanting us to take this a step further and take the x value, which is negative 1, and the y value, which is 5/3, and add them together. Okay, now as you know, common denominators is how we add fractions, but you also have a calculator that will totally just do this for you. You are totally welcome to use that. going to go ahead and go the long way and say negative 3/3, which is negative 1, plus positive 5/3 gives me a positive 2/3. That right there is my true final answer that I would submit if it was on a test or a quiz. 2/3 would be your official final answer. Okay? Alrighty. 2 more problems. Given the equation 2x minus 3y equals 0 and x plus 2y equals negative 7, what would you substitute for x in the equation 2x minus 3y equals 0? So they're saying, what would you substitute for x in this equation? So they're saying, what would you plug in right here? Well, that means I need to focus my eyes on this equation, and solve it, because that is what is going to be plugged in to the other equation. So I'm going to take x plus 2y equals negative 7, and they're saying that we're going to substitute for x. So I need this x to be the thing that's by itself. So I'm going to subtract 2y from both sides, and I see that x is equal to, negative 7 minus 2y. That is what x is equal to, so that is what I would substitute into the other equation. And that best aligns with D. All right, now 12 says, confirm that the solution you found on number 9 is correct by graphing. So number 9 is right over here on the left. So it says x equals negative 5/3 y. Well, we can't graph that. We need to solve that for y in order to get it into y equals mx plus b. Same with the second equation. So I'm going to start just by rewriting those over here, kind of in some more workspace. And then I'm going to work on getting them into slope-intercept form so that I can graph them. Let's change colors here. Okay, so in order to get rid of this negative 5/3, I'm going to multiply by negative 3/5 on both sides. And I see that y will be equal to negative 3/5 x. That'll be my first equation to graph. Down here, I need to add 2x to both sides. So 5y equals 2x plus 25. So y equals 2/5 x plus 5. So these are the 2 things I need to graph on my coordinate grid. I'm going to start with the first one. First one has a y-intercept of 0. So I'm going to start here. And a slope of negative 3/5. That means I need to go down 3 over 5. Or up 3 over 5. I don't have very many points on this graph. Okay, but I know that my solution is supposed to be negative 5/3. Okay, my second equation has a y-intercept of 5. Let me switch colors again. So I'm going to go put a y-intercept of 5, and then it's got a slope of 2/5. So I would go up 2 over 5, up 2 over 5, up 2 over 5, over and over and over. Same with down 2 to the left 5. Oh, and there's that intersecting point right there. So I see that the solution on the graph is negative 5/3, which corresponds with the answer we got by solving for substitution. Okay, so I know that was a lot, but really it's the same skill over and over and over. You can see even just in my work, it looks the same on every problem. So focus on getting your variables isolated so that you can plug them into each other's equations. Let your teacher know if you have any questions.